In this question we have a spacecraft covering a distance of 5 times 10 to the 12 meters in 6.9 years. This spacecraft collects dust particles from the space. When a dust particle hits the gel on the spacecraft, it buries itself in the gel, creating the cone-shaped tract seen on the diagram. So the dust particles will be moving from there into the gel. Then we are told that the length of the track is typically 200 times the diameter of the dust particle. So this distance will be 200 times the diameter. Part A of the question asks us to calculate the average speed of the dust in the Voyage. The equation for speed is distance divided by time. So if we look at the information that we are given, the distance that the spacecraft travels is 5 times 10 to the 12 meters, and the time is 6.9 years. But we can't leave the time in years. We need to convert this into seconds, and this can be done by thinking in 1 year we have got 365 days, each 24 hours, times by 60 minutes and 60 seconds. And this will give you the average speed, which will be 2.3 times 10 to the power of 4 meters per second. In part B, we are asked to find the average stopping force produced by the gel acting on the dust particle. We are given the diameter of the dust particle, its mass, and its velocity, which is the velocity just before it hits the gel. There are a couple of ways of approaching this question, one of which is using Newton's second law, F equals ma. The F here is the resultant force acting on an object, relating it to the mass of the object and its acceleration. In our case, the object is the dust particle, and the only force acting on it is the stopping force by the gel. So the stopping force will be equal to the resultant force on the dust particle. To calculate this force, we need the mass, which is already given to us, but we don't know what the acceleration of the dust particle is inside the gel. So we need to use another equation to find the acceleration. We can use the Suvat equations, or one of the Suvat equations, to find the acceleration. Let's remember that this is the displacement, this is the initial velocity, final velocity, acceleration, and the time taken for an object which is experiencing constant acceleration. Firstly, A is what we are interested in. Then the time, we are not told anything about the time that the dust particle takes to stop, so let's put that as an unknown and see what others do we know. The final velocity is going to be 0 because we are told the dust particle comes to a rest in the gel. The initial velocity is the one given there, which is 6.1 times 10 to the 3 meters per second. And the distance it travels before it comes to a rest is going to be determined from the diameter, because at the beginning of the question we were told that the typical length of travel in the gel was 200 times the diameter. And let's not forget that this is in millimeters, so we need to convert it to meters. Using these quantities, since we don't know the time, we should pick the equation which does not involve time, which is v squared is u squared plus 2is. Substituting the numbers in, we have 0 equal to 6100 squared plus 2a times 0. times 10 to the minus 3. Rearranging for a, we have 6100 squared and the minus in front divided by 2 times 200 times 0.7 times 10 to the minus 3. And this will give you an acceleration which is minus 1.33 times 10 to the 8 meters per second squared. We can now put this acceleration back into the F equals ma equation. So we have the force being equal to the mass 4 times 10 to the minus 6 times the acceleration, which we just found. And this will give you a force of minus 530 newtons. The minus sign shows that it is a stopping force. So we have our force as 530 newtons. The other way of approaching this question is using work energy principle. When a dust particle was moving at 6100 meters per second, it had some kinetic energy. We can find this kinetic energy by using the equation half mv squared. Putting the values in, this will give you half times 4 times 10 to the minus 6 times the velocity squared, giving 74.4 joules. But then the particle comes to a rest. So the kinetic energy will be 0. Since the velocity is 0, the particle does not have any kinetic energy. But where does this kinetic energy go, which it initially had? In order to get rid of that kinetic energy, there must be some work done on the particle. And that work done comes from the stopping force by the gel. Unless there is any work done, the kinetic energy wouldn't have gone anywhere. Remembering that work done is force times distance, we can say that the change in the kinetic energy, which is 74.4 joules, is equal to force times the distance that the particle travels, because the work done should be enough to take all the kinetic energy from the dust particle. But what is the distance that the particle travels? We are told it's going to be 200 times the diameter, and convert it to meters. Rearranging for force gives us 74.4 divided by 200 times 0.7 times 10 to the minus 3, which gives the same 530 newtons.